This video is the first of two videos describing the capabilities of Statgraphics version 20 for accelerated life testing. Accelerated life tests are tests designed to estimate the failure time distribution of products that have lifetimes that are too long to estimate under normal usage. The products are subjected to higher than normal levels of stress during the tests, using one or more accelerating factors such as pressure or temperature. The results are then extrapolated to normal operating conditions using models such as the Arrhenius model. Statgraphics version 20 contains two procedures that may be used for accelerated life test model fitting. The first is the accelerated life test plots procedure. It fits models to estimated statistics obtained at several levels of an accelerating factor. Common statistics are the mean time to failure or a percentile of the estimated failure time distribution. The second procedure is called accelerated life testing. It fits models to observed or centered failure times at selected levels of one or more accelerating factors. This procedure supports any of 7 failure time distributions. This video, part 1, will talk about accelerated life test plots. Another video, part 2, covers accelerated life testing. This is the data that I'd like to model. It consists of failure times of 50 circuit boards. 10 boards were tested at 80 degrees. That's the normal operating temperature. 10 were tested at 125 degrees. Another 10 at 150 degrees, 10 more at 175, and 10 more at 200 degrees. The failure time of each circuit board was recorded unless the board had not failed by 3,000 hours. If it had not failed by 3,000 hours, then it was labeled as censored at 3,000 hours. You notice in this case, at the normal operating temperature of 80 degrees, none of the boards had failed. They were all censored. The same was true at 125 degrees. At 150 degrees, there were 3 actual failures and 7 censored values. On the other hand, at 175 degrees and 200 degrees, all the boards failed. In this video, part 1, I'm going to describe how to use the accelerated life test plot to model this data. Step 1 will be to fit a Weibull distribution to the data at each temperature separately. We'll then, in step 2, estimate the 10th percentile from each fitted distribution. That is the point at which I estimate 10% of the circuit boards will have failed. We'll then fit an Arrhenius model to the estimated percentiles at the different temperatures and extrapolate the fitted model to 80 degrees Celsius. Here I am in Statgraphics version 20. I've loaded the circuit board data into the Statgraphics data sheet. The sheet has 3 columns: temperature, which is the temperature at which each board was tested. The hours column has the time to failure, or the value 3,000 if the circuit board had not failed by 3,000 hours. If the circuit board had not failed by 3,000 hours, the censored column is set to 1. If it failed before 3,000 hours, censored is sent to 0. I'm now going to fit Weibull distributions to each temperature. To do that, I'll go to Describe, Life Data Analysis, Weibull Analysis. The data to be fit are in a column called Hours. The censoring indicators are in a column called Censored. The data are to be grouped by temperature. Now I'm also going to go to the Select field and put temperature greater than 125. That will avoid the temperatures at which there were no failures, where I could not fit a Weibull distribution. Now I'll press OK, and the Weibull Analysis Options dialog box will appear. The Weibull distribution has a lower threshold, a lowest possible minimum value. I can either leave it set to 0, which is the standard case, or I could have the program estimate a lower threshold. I can also pick from 3 different methods for fitting the distributions. I can use rank regression, maximum likelihood, or a Y-Bayes approach where I specify the shape parameter. The default method is maximum likelihood, and I'll ask for confidence intervals at 95%. When I now press OK, I can select different tables and graphs to display. I'm going to ask for the analysis summary and critical values on the left, and on the right for the Weibull plot. When I press OK, an analysis window will appear with the results of the estimation. Let's take a look at some of the output that was generated. In the upper left corner of the analysis window, you see information about the fitted Weibull distributions. We fit a distribution at 150 degrees, 175 degrees, and 200 degrees. The 2 parameters that needed to be estimated for each Weibull distribution were the shape and scale parameters, which you see here. It also shows in the far right the estimated mean and standard deviation at each temperature. The graph that was displayed over here is what's called a Weibull plot. A Weibull plot is designed so that if you are fitting data that follow a Weibull distribution, the points should fall approximately along a straight line. Here you see all of the uncensored failure times, and in fact the data do seem to fall along their respective straight lines, indicating that the Weibull distribution is probably a good fit for this particular data. If I go to the lower left, you can see a table of critical values for hours. In this case, what it's done is taken each of the temperatures and estimated the percentiles of the distribution. The percentiles are actually in the column labeled X, and it's estimated everything from the 1st percentile to the 5th percentile all the way up to the 99th percentile. In addition to the best estimate, confidence intervals are also given for those percentiles. The next thing I'm going to do is simplify this table so it only contains the 10th percentile. To do that, I'll push the right mouse button and go to Pane Options. I'm going to blank out all of the tail area fields except for 0.1. That will leave only the 10th percentile in the table. Okay, so I'll get rid of all of the rest of them. I'm also going to turn off the include confidence limits checkbox, which gives me a much simpler table. I now want to take these results, copy them to the Statgraphics data sheet so I can run the accelerated life test plots procedure. That's easy to do. I'll simply highlight the table, the columns of the table here. There we go. Do a Control-C to copy it to the Windows clipboard. Go back to the Statgraphics data book. Click on column 4, right mouse, paste, and tell it I've got column names, and there's my data. Now I'm going to change the name of the first column. Rather than being temperature underscore 1, I'll make it junction temperature. Okay. I'll right mouse and delete the second column. The X column I double clicked and I'll call it P10 because it's the 10th percentile. I now have 2 columns I need to do the accelerated life test plots. I have a temperature column and a column containing the 10th percentiles. It's now time to fit a model to my percentiles. The model I'm going to use is the Arrhenius model. The Arrhenius model takes the form y equals a times e to the minus capital E divided by kt. In this equation, y is the quantity to be estimated, such as P10. T is temperature in degrees Kelvin. That's degrees centigrade plus 273.15. K is Boltzmann's constant. A and E are 2 unknown parameters. To fit the Arrhenius model in Statgraphics, I'll go again to the top menu, but this time select Describe, Life Data, Accelerated Life Test Plots. The data to be modeled, the dependent variable in my equation, is P10. The accelerating factor I put in a column called junction temperature. When I press OK, I'll see a choice of different models that I can fit. By default, I can fit the Arrhenius model, but there are 5 other models I could fit if the data followed some other functional form. I also need to go down to the checkbox here that says convert accelerating factor from C to Kelvin, because in fact my data are in degrees centigrade, whereas the Arrhenius model expects data in Kelvin. This will allow it to do the automatic conversion. Finally, I'm going to select the temperature at which I want to do my predictions, which is the normal operating temperature of 80 degrees. I'll now press OK, and the Arrhenius model will be fit. You can see a plot of the data over here. It's a specially scaled plot for the Arrhenius model. P10 is on the dependent y-axis in a log scale. On the x-axis, we see a modification of junction temperature, all done so in fact if the model fits well, it will be a straight line. You can also see the prediction of the 10th percentile. At the top it says predicted P10 is 251,418. 251,418 hours. And the red line shows that that is a prediction at, well, it's 80 degrees centigrade when put through that transformation. I can also come back here to the table to actually see the predicted value. Here it is again, 251,418. It also gives lower and upper 95% confidence limits for that percentile. Now, unfortunately, in this case, those confidence limits are very wide. Basically, because all you've done is done a regression with 3 data points and 2 unknown parameters. In such case, you might get a good prediction of the percentile, but the confidence interval is going to be very imprecise. This ends part 1 of accelerated life testing. In part 2, we're going to look at a new procedure that was added to Statgraphics recently. It's actually under the Relate Life Testing menu. What it does is combine the distribution fitting and model estimation steps into a single procedure. It also allows for fitting distributions other than the Weibull distribution if another distribution is more appropriate. In part 2, we'll see that this procedure also handles more than just one accelerating factor. The result is much tighter confidence intervals.